Hi guys, in my previous concept I discussed about motional EMF by Faraday's laws. How it works? Suppose here I am having a setup. This is a bulb and which is connected to a voltmeter. If you take this as voltmeter. Now to glow bulb, current supposed to flow. To flow current, we need EMF, electromotive force. So the EMF we can get from a source, from a cell is a source of EMF. But here we are talking about motional EMF. If this is a conducting rod which is kept in a uniform magnetic field. So if you move this conducting rod, so the motion causes an induced current which flow in the circuit. Now the induced current setups an induced EMF. So the induced EMF direction changes depends upon the direction. So because of that, here we can see the bulb and the voltmeter, so they are working. And we got the final expression, the expression for induced EMF E equal to B times L times V. So B is the strength of the magnetic field and L is the length of the conductor, which is movable conductor, and V is the at what velocity we are moving. And we got the direction of induced current by using Fleming's left hand rule. So today's class I would like to discuss same motional EMF but not by Faraday's law, but it's by Lorenz Force. First of all, recall what is Lorenz Force. Suppose if I take it here, Lorenz force comes into action. Suppose when a charge moves, it's very important, not conductor. So the main thing here I need that when a charge moves. When a charge, either the electron or positive charge or negative charge, for a moment you can take an electron. When an electron moves in a uniform magnetic field, suppose this electron is moving in a uniform magnetic field right at here. Because of the motion of the electron in the uniform magnetic field, over this electron some force will act. So that force due to magnetism, so that force only we call as Lorenz force. The force experienced by an electron or a charged particle when it is moving in a uniform magnetic field. So that force we call as Lorenz force. So in the previous chapter we already derived this expression. Lorenz force F equal to, it's BQV. Here the Q is the amount of the charge and B is the strength of the magnetic field and V is the velocity. And this force is the force experienced by a charged particle in a magnetic field. So that force is known as Lorenz force. Now with the help of the Lorenz force concept, let us try to derive the same expression for the motional EMF. So this is my concept right now, the motional EMF by Lorenz force. Okay, so we take the same figure. It's consider a rectangular frame, conducting frame. So MSRN. So that is the rectangular conducting frame, and here in this rectangular conducting frame the PQ. So the PQ is a movable arm. So this part is a movable arm in the circuit, which can be moved to left to right. Now, if the setup is kept in the uniform magnetic field B, which is right now going inside the screen, then the arm PQ is moved. It can be moved. For a moment, if you take, it's moving towards to left with a velocity V. Now, there you need to do very important observation. If arm PQ moving left, it is moving left. So it's a conductor, so the electrons which are present, electrons will also move left. The electrons which are present in the conductor PQ, they also will move left with the same velocity V. With velocity V. Yeah, this is the very observable point at here. Yeah, it's a common sense. If a conductor PQ is moving towards one direction, the conductors which is having electrons, those electrons also will move to the same velocity. Now, if those electrons are moving in the uniform magnetic field, so what we discussed it here, so Lorenz force will be act. Lorenz force will act on those electrons. So if I take, the electrons experience a magnetic force which is known as Lorenz force. The force due to magnet equal to BQV. So this is the first expression. So to find the direction of this force, so since it is a charge, we will use Fleming's left hand rule. Fleming's left hand rule. Don't be confused with the Fleming's right hand rule and the Fleming's left hand rule. So Fleming's left hand rule is used to find the force for the charges. But Fleming's right hand rule used to find the induced current or force for a conducting rod or for a conducting material. Since it's a charge, so we will use Fleming's left hand rule to find the force. Now the force in this particular direction Q to P, now the free electrons also move from the P to Q. Since the force will be acts from the Q to P, now the direction of free electrons. So the free electrons move from P to Q. So this is the point what we needed. So in this conducting rod, which is moving in a uniform magnetic field, so in this conducting rod, if the electrons are moving, suppose if you can draw that figure. So this is a rectangular frame. So S and R having fixed length of L, and here I am having a movable arm. So this is my movable arm. So this can be moved in a uniform magnetic field. If I call this movable arm PQ, and this PQ is moving along left direction for an instant. So it is moving along this direction with the velocity v. Since it's moving along this direction, the electrons which are present within the conductor of the PQ also move. Since electrons are moving, so it contributes current. So if they are moving from P to Q, it means at here negative charge accumulates at P and positive charge accumulates at Q. So when the free electrons move from the P to Q, so negative charge accumulates at P side, negative charge accumulates and positive charge accumulates at Q. So this is what we need. So if I label it here, so here the negative charge is accumulating and here the positive charge accumulating. So if the negative charge accumulating at here and positive charge accumulating right down at there, so we can expect an electric field E is set up in the conductor from Q to P. Yeah, because of the charge separation, an electric field is set up at Q to P. So because of the motion of this PQ conductor in the magnetic field, obviously in the conductor having electrons, they also will move. Now the electrons are moving from the P to Q, so negative charge accumulates at P and positive charge accumulates at Q. So this causes an electric field. An electric field E will set up in the conducting rod PQ and that electric field direction from Q to P. Because at Q positive charge is there and at P negative charges accumulate. Now if you can know clearly, so because of this electric field, so there is a force. So the electric field exerts a force. So that is the force due to electric field, which is known as, we know that charge times electric field, or this is also nothing but Coulomb force. There is a Coulomb force which exists on the electrons in the electric field. Now the accumulation of the charges at the two ends, from the P end to Q end, they will continuously move. How long they will move? So the accumulation of the charges continuously moves till the accumulation of charges moves till the two forces are balanced. So here what are the two forces? Here the two forces, nothing but the force due to magnetic field, Lorenz force, which equal to the force due to electric field. So how long these two forces gets balanced? So till that time the charge will flow. And if we can make it equal, these two forces, F equal to, we got it, QVB. So here it gives to that Q times E. And you can cut that like terms, Q and Q gets cancelled on both sides. So we can end up, so V times B equal to E. Now, if you remember, we have a very helping formula, that is the potential difference. We can express the potential difference in terms of potential difference V equal to E times D. So this is the expression for the potential difference in terms of electric field and the distance. So to find the potential difference between the P and the Q, so I need to know what is the electric field and I need to know what is the distance between the P to Q. So here the distance between the P2Q is nothing but L. So this formula gets converted as the potential V equal to, since here distance between P2Q equal to L, so this formula I'd like to rewrite that as V equal to E times L. So from this first equation, suppose if you can call this as another equation A, you can substitute this equation A in this equation B. So A in B, therefore we got it a new expression that, now if we can write this as V equal to BVL. So don't be confused, here the V means this V is nothing but potential difference. So this is potential difference, and another V, so this I supposed to mention as a little, so this is known as V is the velocity. So here also I can change that, so here the V is velocity. So little v equal to velocity and capital V is potential difference. Don't cut the two terms. So now to get the potential difference between the ends of the PQ equal to V equal to BVL. Now clearly this potential difference only we known as EMF, or this magnetic force which is moving on the free electrons, that magnetic force will maintain the potential difference, and this potential difference produces motional EMF. Therefore motional EMF E equal to, we can write that as BV times L. So here B is the strength of the magnetic field and V is the velocity and L is the length of the conductor. So this is the same expression we derived by using Faraday's law. So but the same expression here we derived by using Lorenz force. So what is the Lorenz force? Lorenz force is a force which is experienced by a charged particle when it is moving in a uniform magnetic field. So let's do further. Suppose since I got an EMF expression, so this is EMF expression, EMF E equal to BVL. So here V is the velocity. Since EMF I got, I would like to find the expression for current I. Suppose the rectangular frame MSRN having a resistance, the frame MSRN having a resistance of capital R, and PQ arm is also included, but we can take PQ is having negligible resistance. So if we can neglect the PQ arm resistance, so neglect PQ arm resistance, therefore the total resistance equal to R. The total resistance of the frame equal to R. That's the final. Therefore total resistance of the frame, that is P which equal to capital R. Now to find the current, so here I need to find the current. So how we can get the current value? Current I equal to EMF upon resistance R. So now we got the EMF value equal to BVL upon R. So this is the expression for current induced in the loop or induced current. Current induced in the loop, here the loop is PQRS. Now if current induced in the loop equal to BVL upon R, and we learned that the arm P2 is experiencing a force. Now let's try to find the expression for force on the movable arm. So because of the Lorenz force, the conductor PQ of length L and carrying a current I will experience a force in perpendicular magnetic field. So this also we derived in the earlier concept. The conductor PQ of length L, so it is moving with a velocity v and carrying current, it's carrying current of I will experience a force. It experience a force, that force is F. Since the conductor is moving perpendicular to magnetic field, suppose if I write that expression, the force F equal to BIL sine theta. Since the arm is moving perpendicular to magnetic field, therefore theta in this case equal to 90 degree. Now if you can substitute theta equal to 90 degrees, the force F equal to BIL sine 90 degree. So here we can get F equal to B times I times L. Now from the above expression, substitute I equal to BLV upon R. Since I equal to BVL upon R, what I derived just above, therefore the force F equal to, so B times L of BLV upon R. Now the force experienced by the conductor equal to B square times L square times V upon R. So here V is the velocity of the moving arm. And L is the length of the moving arm, and B is the strength of the magnetic field, and R is the resistance of the the resistance of the rectangular frame. So this force acts in a direction that opposes the velocity of the arm according to Lenz's law. So this is the force which is experienced by a moving arm PQ in a magnetic field. So what is Lenz's law says? Lenz's law says that always opposes the cause. Now here, if the arm is moving towards to right, and the force will be acts towards to left. Again I am repeating, if the arm is moving with a velocity towards to right, and the resultant force on this moving arm will be acts in the leftward direction. So that is according to Lenz's law. Now I need to derive one more final expression. That final expression is power. Power delivered by the external force. Power delivered by the external force. Now the power supplied by the external force to maintain the motion of the movable arm is, we can write that power P equal to the product of the force times velocity. So here F equal to force and V is velocity. So the power supplied by the external force to maintain the motion of the movable arm. Yeah, the external force should apply power on it. Why? Because the because of the Lenz's law, when velocity of the arm towards to right, there is a force which is acting in the opposite to the velocity. Now that force causes decreasing in the velocity. If the velocity decreases, the induced current decreases. That should not affect. So to maintain constant velocity, the external force should apply power. So here what is the power delivered by external force, not which is coming from the induced current or anything else. So this is the power delivered. At what power you are pulling. So to get the expression power P equal to the product of the force times velocity V. So we got the expression force F equal to, above it is there, B square L square V upon R times multiply with the velocity at here. So this expression changes B square L square V square upon R. So this is the power which should be delivered to the movable arm. Now, if that is the power, we can get one more expression, that is power loss. Power loss as joule loss. What is this power loss? Since two forces are acting in opposite direction, one is the force applied due to the external force to make the arm move, and one more force is the Lorenz force which makes the arm which is a left side. So here the two forces are acting. When the two equal and opposite forces are acting, not only equal but opposite forces are acting, so that causes some power loss at here. So the power dissipated means the power wasted. The power dissipated in the loop as gives heat. Now the power loss, power dissipated. The power dissipated in the loop as joule heating loss. So we know that power due to joule, so power P equal to I square R. So we got that expression, current I equal to BVL upon R whole square times R. So the power loss in this case equal to B square L square V square upon R. It means when arm is moving in a magnetic field, when this rectangular arm is moving in uniform magnetic field, induced current setups, because of the induced current, induced EMF setups, and because of the induced EMF, and there is a force on the movable arm, and that force will act opposite to the applied force, And because of these two forces are acting opposite in direction, there is power loss. So that power loss comes out in the form of heat. So here everything you can see the mechanical energy. Here why is the mechanical energy? To move the arm PQ we require mechanical energy. The mechanical energy expended to maintain the motion of the movable arm is first converted into electric energy because the induced EMF and induced current, and then it converts into thermal energy. And this is also consistent with the law of conservation of energy. So to prove the law of conservation of energy in this case, how the mechanical energy is converting into electric energy and heat energy. So we will prove with the help of the Lorenz Force altogether. So finally, as a conclusion, we can say that motional EMF from Lorenz Force. Motional EMF from Lorenz Force gives the conclusion of conservation of energy. Energy gets conserved. Conservation of energy. So in this conservation of energy, so the case is a arm is moving in a magnetic field, uniform magnetic field. It's a conducting arm. How the energy gets conserved at here? First, whatever the energy we are giving, so that is mechanical energy. So here mechanical energy the mechanical energy first converts into electrical energy, and again the electrical energy converts into heat energy. So if you can see that, so here the force which is applied in the one direction, because of the force induced current setups, and induced current causes an induced EMF. So the plus and negative sign shows the induced EMF. So if you can take the magnetic force, here you can see two forces are acting. One is the force applied by me. So the hand which is applying a force, so that is the mechanical force. And the second force is coming to action, that is the magnetic force. So this magnetic force always acts opposite in direction of the applied force. So to find out the magnetic force, we are using the Lenz's law. Now to maintain the constant velocity, so these two forces, the applied force should be equal to magnetic force. So now in that case we are reaching a conclusion that the moving arm will lose power. So that power will be in the form of Joule's law of heating. So as a conclusion I can say that whenever you apply a force in the moving arm in right side direction, there is a force which come into action. That force is known as magnetic force. So the expression for the magnetic force, we derived that force F equal to BVL sine theta. So here theta equal to 90 degree. So we got the expression from that above derivation, that equal to B square L square V upon R. So this is the force which is acting on the movable arm. So that force is magnetic force, and whatever you are applying, so that is applied force. So as a final conclusion, this concept leads us to conservation of energy. The mechanical energy converted into electrical energy, then heat energy. This is all about the concept of Motion EMF from Lorentz Force.